Seth Heitfield is a research scientist in the Computational Sciences and Engineering Division at Oak Ridge National Laboratory. His research focus at ORNL includes software-defined infrastructures for science federations and energy systems and signal processing on high-performance heterogeneous embedded systems. Prior to joining ORNL, he earned his PhD and MS in computer engineering from Virginia Tech. His research focused on wireless communications security, where he developed architectures for secure software radios using a defense in-depth approach to protect system components from exploits. While at Virginia Tech, he also worked at the VT Ground Station and Space at VT on several CubeSat projects that are currently in orbit. Please welcome Seth Heitfield.
Hi, I'm Seth Heitfield, and today I will be giving an update on some of the GnuRadio work that our team at Oak Ridge National Lab has been doing for the DARPA DSSoC program. Just a little background on myself before we begin. I recently joined the lab as a research scientist in the Computational Sciences and Engineering Division, and prior to that I was finishing my PhD at Virginia Tech, where I was focusing on security for software-defined radios. Here's a quick outline of my talk today, and we're really going to focus on the programming systems and runtime systems work that we have been doing. We'll also talk some about the example target application of workflows that we have been using to demonstrate how some of this work can be integrated into the GnuRadio ecosystem. Over the past few years, we have seen a massive shift in computing towards extremely heterogeneous systems, and this trend will only continue to grow. We do see a lot of benefit from moving towards these systems in terms of high performance and reduced power consumption because we can offload the applications and workflows ill-suited for running on a CPU to hardware that is specifically designed for that application or for that purpose. For example, in the mobile computing world, many of the devices and functionalities of those devices, such as the wireless connectivity, video processing, some of these things have been offloaded to coprocessors rather than executing on the main host, just in terms of better performance and better battery life. However, as things become more complex and more heterogeneous, there is this massive trade-off in terms of the software and infrastructure and the complexity of that in being able to fully utilize these devices. Here are some quick examples of some of the systems that we have been testing with as part of this work. These are all systems available through the Experimental Computing Lab at Oak Ridge. The Summit Node and the DGX workstation shown here are examples of the high-performance class and cloud computing class systems. And the Summit Node is an exact copy of the hardware that is actually used within the OLCF's Summit supercomputer. Another example of a heterogeneous system that we've been looking at, specifically for mobile computing, is the NVIDIA Xavier SoC. This system includes an octa-core ARM CPU, as well as a GPU, deep learning accelerator, a vision accelerator, and several other types of multimedia accelerators. The Qualcomm Snapdragon is also a similar system for mobile computing that is also very heterogeneous. One interesting feature of this processor is that the CPU cores themselves are even heterogeneous and use the ARM Big Little architecture. All of these example heterogeneous systems really raise the question of how do we best utilize these systems? These typically have multiple processors, multiple types of processors, different interconnects, and each of them likely have a different programming model, which there becomes a lot of complexity in how you best and how you efficiently use those resources. One of the big issues is that we see this productivity versus performance trade-off. Programmers and engineers are going to have a large cost in terms of getting up to speed with the different programming models, and that is going to reduce their overall productivity because these accelerators may be very different from a traditional CPU programming model. So the goal of our work is really to simplify this process of integrating these accelerators into these different applications. Are there ways of hiding these complexities so that the programmer doesn't need to be concerned about the specific programming models of an accelerator? And once we have hidden these complexities and we have codes targeted towards those accelerators, how do we efficiently and intelligently offload these onto different heterogeneous devices? We're really trying to look at this from a full development lifecycle. Given the applications, can we break these applications down using ontologies into understanding all of the different methods and computations that are occurring within those applications? And based on that, and targeting and looking at off-the-shelf hardware, how can we map those applications with a given programming system and a given runtime scheduler efficiently onto the hardware so that we can accelerate that application? As I mentioned before, one of the biggest issues with heterogeneous systems is understanding how to program the different accelerators and their given programming models. With our project, we're trying to help simplify this through the use of the OpenARC compiler and OpenACC. OpenACC is an open programming standard for accelerators that uses a directive-based approach. Now, this directive-based approach allows a programmer to provide hints to the compiler that allow the compiler to determine what parts of the code can be accelerated and how that code might be accelerated on a target device. And the benefit of this is it allows the programmer to do this without having to modify or adapt the code to target the device in question themselves. Our OpenARC compiler is a high-level intermediate representation compiler that uses OpenACC and provides source-to-source translation from the input OpenACC codes to the codes specific to a given accelerator. So, for example, there can be several target architectures such as NVIDIA or AMD GPUs, different FPGAs, and what OpenARC is able to do is take this original OpenACC code and then compile it to the proper source code that can be compiled by that device's given runtime. And this is very useful for studying different directive-based accelerator computing. So the high-level representation is easy to understand and transform the program input. And there are various passes that can be done in order to determine the best way to program and best way to generate code for a given accelerator. This is an example of what this mapping strategy can look like. In this situation, we can have a singular OpenACC-based GnuRadio block that when passed to the OpenARC compiler, the compiler can actually output several different target source codes for whichever devices are available on the system. So in this case, you could take this original OpenACC block and generate a CUDA variant or an OpenMP variant for running on the CPU or an OpenCL variant for running on an FPGA or a GPU. This is an example of what an OpenACC GnuRadio block might look like. So in this case, we have a GRACC base class, which the block inherits from. And this allows us to do some things such as initialize different parts of the OpenACC backend and the runtime to make sure that thread safety is satisfied for accessing data within the block. Included here, we also have the reference CPU implementation, which is from the original GR blocks that may have already been vectorized. And we also have the OpenACC accelerated version. Now, there are some specific tasks that the OpenACC version does when executing, such as copying data from the input buffers to device memory, executing the kernel, and then copying data back. And when using OpenARC, this block gets translated to multiple different programming models based upon the devices that exist in the system. And again, the main entry function to the system would be the work function of GnuRadio and the GnuRadio block. So every time the work function is called by the scheduler, depending on the context, the OpenACC runtime can determine whether to execute on the CPU or whether to execute on the target device. Here's an example of the performance that we might get using OpenACC to accelerate a block such as the FIR filter block. So in this case, we ran this with a reasonable filter size tap of just 64 taps. And we have a offloaded GPU version. And this GPU version has to do memory transfers between both the CPU and the GPU. And it's interesting, and as we've seen before in the community, there's a trade-off where the GPU version might actually be slightly slower than the CPU version until a certain point where the buffer sizes are large enough that you actually gain performance by offloading the larger buffer sizes to the GPU when doing this execution. So at this point, as long as the input buffer size is greater than about 2048 samples, the OpenACC version will outperform the original CPU version. Until that time, the CPU version can actually outperform the ACC version just due to the overhead of the memory transfer and the kernel launches. After we use OpenARC to generate these different output blocks for given target devices based upon our OpenACC input block, the next step is being able to intelligently determine where and on which accelerators these modules should run in order to gain the best performance. And this is where our Iris intelligent runtime system comes in. The goal of the Iris runtime system is to provide programmers a unified task-based environment that allows them to write portable code for multiple heterogeneous architectures. Currently, Iris is capable of running all the way from an embedded system on a chip, such as the NVIDIA Xavier, to leadership class supercomputers such as OLCF's Summit system. It gives you a graph-style task scheduling system where tasks are units of execution that can be scheduled for any specific device. There are different selection policies and scheduling policies that can be applied to these tasks, and it also provides you a shared virtual device memory so that there is memory consistency throughout the entire system. And we've also started integrating this with GnuRadio in order to be able to support GnuRadio running on these different heterogeneous systems. The Iris architecture can be characterized in these 4 ways. First, it executes as a single node system with the host CPUs and multiple connected devices. Now, these compute devices can be GPUs, FPGAs, and other accelerators, and any combination of those. It also uses a consistent memory model where there is a separate host space and the shared device memory space. And all of the devices, all of the connected compute systems share this memory space so that Iris can control memory consistency throughout an application's execution. The execution model is this task-based parallel execution where any of the individual tasks can be scheduled on any of the compute devices that are connected to the system. And finally, the programming model is through the OpenARC programming system. In that situation, we would have OpenACC blocks that can be then compiled, and the compiled blocks can be pulled into the Iris runtime for execution. It also has the lower level support where developer could write specific code to target a device of their choice. Task scheduling with Iris is handled with multiple in-order commands. So a task itself is a simple scheduling unit, and there are multiple commands such as the kernel launch command and memory commands that can be executed for each task, which handle moving device memory to the host or host memory to the device. Another key to take from this is that each task queue can have a specific device selection policy. Some of those policies include a developer requesting execution on a specific device type, such as a GPU or an FPGA, or you can specify things such as ontology or locality-aware device policies. And the Iris runtime will then choose the proper device to execute based upon, for example, a given ontology of an application or where the data dependencies exist and on which devices that data is valid for. Iris's memory model allows it to handle memory consistency while executing a specific application. What this simply means is that if there is a data dependency between 2 tasks and a programmer has set a policy for executing one task on a specific device, the runtime will automatically determine that a memory movement needs to occur between the 2 devices and will trigger this memory movement before executing the next task in question. So for example, on the right, task 0 may be executing on the NVIDIA GPU, and task 1 would be executing on an ARM CPU, but the Iris runtime understands and can automatically transfer memory from the GPU to the CPU before executing task 1. Another interesting aspect of the Iris device selection policy is the locality-aware. Now, very similar to the memory consistency model, this in turn allows Iris to specifically pick a device for executing a task based upon where memory was last used within the system. So in this situation, the data from task 0 is the dependency for task 1, and because this data already exists on the NVIDIA GPU device, Iris will already schedule task 1 to also execute on the GPU to maintain the locality of that data and not require a memory transfer. The last main focus of our work for this program is understanding end-to-end SDR applications that can make use of our programming and runtime systems to execute on these heterogeneous systems. One of our goals in choosing specific end-to-end applications is to really demonstrate the entire framework, including the programming systems for OpenARC and the Iris Intelligent Scheduler, running for a real-life SDR application on an example heterogeneous system of interest. And when choosing these, we need to make sure that the applications we choose are scalable, because we want to be able to execute these on embedded systems all the way to leadership class computing systems, and that these systems are easy to understand from an implementation perspective and easy to verify to make sure that everything is running successfully. To that end, we've chosen really a signal detection, classification, and processing example to really draw out these benefits. Mainly, we're focusing on multi-channel broadcast FM. The FM signal, the analog FM signal, is not a very complex signal. However, it gives us a very large amount of parallelism in the number of channels that we can begin to process. So for example, there are 101 total different channels. Each of those channels can have multiple types of output. You can have the mono signal, the stereo signal, the radio data service signal, and even HD radio. And each of these signals becomes more complex for each of these outputs. So there's a lot of simultaneous demodulation and simultaneous processing that we can do for each of these channels. And it's very flexible because we can scale the number of demodulated channels based upon available resources. The larger the system, the more channels we can process. And it's also flexible in the sense that we can demonstrate processing different outputs. And each of these, as I said before, each of these outputs becomes more complex. So it gives us a lot of flexibility in how we can set up our system. For example, we can use a lot of dynamic behaviors. We can look at detecting the active channels and only allocating resources to demodulate those channels at runtime. And then we are not wasting resources on inactive channels. We can also switch the active output based upon the signal environment. So for example, we could process the high definition signal if the signal to noise ratio is high enough, and if it is not, we could drop back to either the stereo or even the mono signal. So this gives us a lot of dynamics in how we can design this application and a lot of flexibility in how it can be implemented. And in the future, we can even look more at doing machine learning for signal detection, using direction finding with MIMO input. So there's a lot of flexibility in how this end user application can execute. So really quickly, here is an example of our transmitter flow graph, and this is just the simple mono signal. So in this case, we have multiple channels that are being piped in, and this allows us to generate synthetic input. So that's another aspect of the system, is that we can very easily generate synthetic data that can be used for our demodulation step. And this is just an example of our receiver flow graph. And the goal here is to really process as many channels simultaneously as possible. That way we're making full use of the accelerators, and that we're trying to utilize the resources available on our heterogeneous system as much as possible. So based on this, we have been able to start replacing different blocks within this flow graph with OpenACC accelerated blocks. Now we're mainly focusing on integrating just the mono signals right now, but going forward we'll be increasing this to include the stereo, the radio data service, and the OFDM-based high definition radio signals as well. But as we started integrating these OpenACC GR blocks into the system, this started showing several integration issues, mainly resulting to resulting to buffering. So for example, handling buffer management within an accelerator can be very difficult. And this goes back to some of the work that I've previously done with custom buffers, which we'll talk about in a second. But in this situation with the GnuRadio runtime, memory for each of the buffers is allocated by the runtime. However, buffers for accessing a specific device might need to be allocated through the framework. So for example, for an NVIDIA CUDA device, through the CUDA runtime. So this increases and causes this double copy problem between the GnuRadio buffers and the buffer for the given accelerator. And this double copy problem can definitely cause a lot of performance overhead within the system. So for example, the basic memory management that we can do for an OpenACC-enabled block is when each block's work function is executed, we can then copy device memory from the GnuRadio block to the device. And then of course we'll have to copy it from the device back to the GnuRadio buffer. And then for a second block, we'd have to do the same thing. So this incurs an additional copy between the device memory and the host memory just to go between two sequential blocks in a flow graph. This can be optimized in a situation where both blocks exist on the same device. That memory copy between the device memory and the host memory can be removed, and then the devices can just pass data through between each other as long as they're on the same device. However, this still doesn't solve the issue that there needs to be an initial double copy to get the data from the GnuRadio flow graph to the device kernels and to the device before each of these kernels can execute. And like I said before, this is really what is a motivating factor for some of the existing work that I've worked on at Virginia Tech. So one of my roles is pulling these custom buffers and integrating these custom buffers that I previously worked on into some of our demonstrations and examples to show the benefit of how this can remove the double copy in the system. So in this situation, this requires some changes to the GnuRadio runtime, which allow the blocks themselves to tell the runtime that they need to allocate and own their own buffers. So these buffers can be created by the blocks, and then a buffer pointer is passed back to the runtime. And then the runtime at that point can manage the samples and the pointers that are going through each of these circular buffers. And in some cases, this also brings up the issue of memory mapping with the doubly mapped memory buffers. So that's something that the scheduler needs to guarantee that the memory pointers are valid when calling an accelerator function. So that is something that has to be considered when building these buffers. The advantage of having GnuRadio's custom buffers, again, allows the blocks to allocate their own specialized buffers, which means that, for example, using NVIDIA, you could use the NVIDIA runtime to allocate the CUDA buffers, and then the GnuRadio runtime can write from the previous outputs in the previous block output, can write directly into those buffers, thus removing the need for the double copy from a GnuRadio buffer to a accelerator's runtime buffer. One of the goals of this project at Oak Ridge is to really integrate with the GnuRadio community and collaborate and hopefully bring some of this work and experience that we've had on this project back to the GnuRadio ecosystem. So this includes doing things like working with other performers in order to integrate the ideas of custom buffers into the GnuRadio runtime so that it can be beneficial to all kinds of different accelerators. Also, that includes the ideas of block portability and concepts we learned from there and how to best target GnuRadio blocks to other accelerators very simply. And lastly, being able to integrate some of the concepts from the iris scheduling and the different things we've learned there into the future GnuRadio schedulers and runtime. So in summary, we talked about OpenARC, which is our programming system that uses a directive-based high-level programming model that allows for seamless porting of applications across different heterogeneous devices. And this really simplifies the workflow of being able to include different accelerators into a flow graph when you write GnuRadio blocks using OpenACC. The intelligent runtime system Iris provides us this unified task-based environment so that we can write code that is portable across multiple heterogeneous systems. We also have our end-to-end example multi-channel simultaneous FM receive. Now this gives us a very simple flow graph that is both flexible in the configurations that we can use and the outputs that we can demodulate, as well as a scalable flow graph in the sense that we can scale it to many channels at a single time. So that can really demonstrate the benefits of using things such as the OpenARC compiler and the Iris runtime component on these extremely heterogeneous systems. And last, our goal is to really integrate this work that we're doing at Oak Ridge into the GnuRadio community through things like the custom buffers work and taking lessons we've learned from the OpenARC and Iris programming system and runtime systems and applying that to the future GnuRadio runtimes and schedulers.